Welcome to a brief video describing the results of FPath Experiment 012. FPath is my project name for experiments on the Feynman Path to Nanotechnology. And what is the Feynman Path to Nanotechnology? Well, it is the idea that you have large machines make smaller machines, which in turn make smaller machines, and so on, until you reach the point where you can reliably move atoms about at the nanometer scale. Of course, the FPath project is nowhere near that yet. It is now operating on the sub-millimeter scale. This experiment expands on the Graphical Stigmergy techniques documented in previous experiments, which use low-quality hardware and closed-loop feedback to control probes operating at the sub-millimeter scale. The videos for Experiment 010 and Experiment 011 would be very useful viewing. A link to those videos is in the description. As a quick recap, Stigmergy is the name for a technique whereby various agents communicate by modifying their environment and leave traces that stimulate subsequent actions by themselves or others. In Graphical Stigmergy, the communication is achieved via different colors on a virtual overlay of a real-world video stream. Here we see a simple probe following a virtual green path left to right. The path does not actually exist. It is overlaid on the screen, but the software treats it as if it was real. As we shall see, this opens up a number of interesting possibilities. The red dot is drawn by image recognition routines, and it locates the tip of the probe. The control system tries to move the red dot, and hence the probe, to the nearest green point. As we get close, other code erases the nearest green point by rendering it transparent. This causes the control system to find another next nearest green point, and hence we get path following as a complex emergent behavior from simple actions. Note that we simply stop at the end when we run out of green dots to find. Okay, so far, so yesterday. Nothing new here from Experiment 010. Let's introduce the concept of a return path here. So what if, instead of rendering the path pixels transparent as we consume them on our way along the path, we instead just change their color? For example, we could make them blue. They are no longer green, and so as far as the path following algorithm is concerned, they do not exist. When we hit the end, it is a simple matter to say, no more green pixels? Well, then go to the nearest blue pixel. If we do this, we get a reciprocating traversal of the same path. We can, of course, change the blue pixels back to green as we go along, and hence our probe can oscillate back and forth along the path indefinitely. Please note that the delay at the end of the path is not due to the software trying to figure out what to do. That action is practically instantaneous. The delay is caused by the change in direction of one of the stepper motors, and although it is running full out, it is spending a lot of time sucking up the slop and play in the inexpensive XY stage. However, do notice how accurate the track following has become. The wire here is 90 microns in diameter, and you can see the calibration scale at the bottom of the image. I have improved the XY stage somewhat. It is still built out of Lego and El Cheapo stepper motors, though. The improved line following is really due to an improved optical feedback system. So now we have introduced repetitive reciprocating motion into the virtual stigmergic path. You can see that it is a pretty straightforward extension of the original concept. Once again, a complex behavior emerges from simple actions. Really, all we have done here is replace the green pixels with blue instead of erasing them as we get near them. Then, when we run out of green pixels, we start looking for blue pixels. You will note that the software controls have changed considerably between the first and second video. Here's what they look like in the first clip without the reciprocating motion. You can see quite an array of options controlling things like probe speed and seek color and a checkbox which activates the process. The video documenting the reciprocating motion has none of those options. It has just a simple toggle button with a label which alternates between behavior stack not active and behavior stack is active. As a general rule, when complexity like this disappears, it usually just means it is moved somewhere else, and this is certainly true in this case. The previous screen control mechanism was becoming increasingly unusable for complex operation, so the code was reworked so that it contains a stack of modules, each module of which controls one specific part of the problem. Each module makes a decision about what to do, and modules further down the stack can override the decisions of the modules higher up on the stack. By the time the control flow reaches the bottom of the stack, the decisions about what actions to take have been made, and the commands are transmitted to the client to implement. if we call these modules behaviors and the stack layers, then it is easy to see that what has been built is really just an implementation of Rodney Brooks' subsumption architecture ideas of the mid-1980s. I put a link in the video description, but the basic idea of the subsumption architecture is that a complex overall behavior is decomposed into multiple independently operating modules. These behavior modules each have a single purpose, and each remembers and adjusts its own internal state as well as various global state variables that determine the overall behavior. Since they are processed strictly in order, the behaviors lower on the stack can also modify or inhibit the actions of higher level behaviors. I don't want to go into great detail regarding this subsumption architecture implementation. I intend to do a full video discussing it. However, consider the actions in the previous reciprocating motion video when the probe reaches the end of the virtual path. The probe is following the virtual line by looking for the next green pixel. It replaces any green pixel it gets near to with a blue tracker pixel. Something has to tell the overall behavior to look for green and leave blue. When we reach the end, something has to detect that there are no more green pixels, and then trigger the hunt for blue pixels and then leave green pixels. Done in the standard way, even this simple example would require fairly intricate nested if statements. Done with a subsumption behavior stack, we just have a behavior module that continuously outputs the seek color contained in its internal state. We have another that outputs the replacement tracker color, and yet another that counts the remaining current seek color pixels, whatever color that might be, and then another that triggers the switch in the seek and tracker colors. The resulting action is a composite of all these behaviors. And this is just the decision to control the seek and tracker colors. There are other groups of behaviors in the stack. For example, some manage the image recognition to identify the tip of the probe, and others to control the motors. Turns out that a behavior stack like this is very useful for implementing complex behaviors. Online you will read that there are some architectural criticisms that the inhibition mechanism reputedly does not work very well in a distributed system. I believe I have managed to address that issue. In the Walnut control software, the same behavior stack runs on both the server-side Windows PC system and also on the client-side Linux BeagleBone system. The information and state variables are nicely and near instantly shared between the two. The two systems are effectively one merged behavior stack. But I am digressing off the main topic and into the realms of software design. As I mentioned earlier, I will produce a video devoted to the distributed FPath subsumption architecture so that the people who are not interested in such things do not have to sit through a computer science lecture. So, why is the subsumption architecture a more functional solution in this case than an alternative such as a nested series of if statements? Well, let's do something more with our virtual line following behavior. To this end, I have added a red LED to the work surface. This red LED can be turned on and off manually by clicking on a control on the screen, or it can be turned on and off via automatic signals. The LED is an 0805 surface mount and hence is 2 mm by 1.25 mm in size. You can see it at the upper left of the screen now. I am pressing a control on the Walnut software to manually blink the LED. What if we can embed commands into the Graphical Stigmergy idea? In other words, besides just being a path to follow forward and backwards, perhaps the virtual path can itself encode actions. Note the slightly darker bit of the path. This is the control area. It really should just be a different shade of green, and the software considers it to be such. The different visible color is just Microsoft messing me up, and I can't be bothered to code around it. Not the first time this sort of thing has happened, I can assure you of that. Anyways, back to the point. When the probe reaches the control area, the behavior stack knows to activate the red light. We are using the LED light as an easily visible analog for any electrically controllable actuation. You can see it happening now. When the probe passes out of the control area of the path, the LED light turns off. Thus, the path is controlling the action. To understand how this works, let us digress once again for a moment and explore how the embedded command activation is implemented. To do this, we need to launch RetroCAD. In general, the colors in a screen pixel are represented by a 32-bit integer. Put enough pixels together and you get an array which represents an image, and the Walnut software can easily process each pixel in the array. 32 bits are 4 bytes. 3 of these bytes are used to encode the red, green, and blue color combinations, RGB, that you may be familiar with. Each byte can contain a value between 0 and 255. Here we have a 32-bit integer representing a green pixel. The G byte is the only non-zero value. But this leaves one byte spare. The high byte is typically used for something called an alpha channel, and this is usually used to indicate the transparency of the pixel when it's merged onto other pixels. Like the R, G, and B bytes, it can have a value between 0 and 255. It is up to the rendering software what it does with the alpha channel. It can ignore it entirely or use any one of a number of standard or non-standard algorithms to combine the R, G, and B colors of 2 pixels. In this experiment, we are not all that interested in what happens when we merge pixels. Instead, what we do is use the alpha channel to encode a byte, which triggers the probe actuation. So let's encode a value of 254 in the alpha channel instead of 0. As the probe travels along the virtual line, cheerfully moving our red dot onto green, we also take note of any alpha channel values under the red dot. When a specific alpha value is hit, 254 in this case, a behavior triggers the LED activation. So the activation command is embedded in the path and the software does not have to do any complex planning or visual recognition. Simple behavior modules just need to react and a complex overall behavior emerges from that interaction. More specifically in this case, a behavior fetches and processes the alpha channel value and notes down what it sees. Another behavior monitors the alpha channel value, and if it sees a matching trigger value, it sends a signal to turn on the red LED. Each behavior mindlessly does its own little thing and moves on. The complexity of the resulting actions is an emergent property of the interaction of each individual behavior. To see the utility of this system, we can extend it by adding multiple commands to the virtual path. Here is a path with 4 embedded commands. As the probe moves along, we are effectively blinking LED without having added any extra control code to do this. Here is a more intricate example of a path with an embedded command. You'll note that if we are seeking green, we flash the LED while over the embedded command, as we did before. However, on the return path, when we're seeking blue, we ignore the red flash on the center embedded command and instead trigger a desire to seek the color red. This, of course, moves us on to a completely different path. Note that only a very modest amount of extra control code is required to add complex behaviors such as this. Basically, the behavior modules just stack up, kind of like software Lego bricks. New ones can be added to the stack to enable whatever behaviors you might wish to have. In order to implement the above actions, I just added a simple behavior to the stack that, when triggered on the matching alpha value and when blue was also the active seek color, it inhibited the red LED activate and switched the seek color to red. Note the previous flash the red LED behavior is still present in the stack and operational. Its actions were just overridden, subsumed, by a later behavior. This is the essence of the subsumption architecture. So we have graphical stigmergy with embedded commands. The action command is contained within the path, and the software does not really have to do any complex planning. It simply reacts. The subsumption architecture handles both the higher and lower level behaviors quite well. As mentioned earlier, the red LED is really just a stand-in for any type of actuation which might be needed. I'll show you a brief example clip of an actuated probe I built. You can see the bent tip of the probe is discovered by the image recognition system in a similar way to that of the straight probe. A red dot is placed near the bend in order to provide a consistent recognition point. When the red dot hits the embedded command area, the probe automatically flips from pointing left to pointing right. Due to alignment issues, the flip also drops the bend of the probe below the virtual path, and the motor control behaviors need to compensate to get the probe back onto the path. As before, the slight pause after the flip is caused by one of the stepper motors switching directions, and the delay is due to the slop and play in the gearing being sucked up. Ultimately, the behavior stack which controls the stepper motor which performs this flip is just a minor variant on the stack which switched the red LED on and off. Well, that's all for now. I just thought you might be interested in how embedded control commands can be used with graphical stigmergy techniques and closed-loop feedback to enable low-cost hardware to move and actuate a tool at the sub-millimeter scale. Thanks for watching, and see you next time.